So welcome back, children. Let's continue our discussion on Gauss law. So we talked about the Gauss law yesterday, and then we said that the Gauss law tells you that the amount of flux that is coming out of any closed surface is equal to the charge enclosed in the surface divided by epsilon naught. So that was the Gauss law. I'm going to expand a little bit further so that we understand it a little deeper, and then we'll go on to do some problems using the Gauss law. Okay? It's this. First, let's imagine that you're going to have a simple charge Q, a point charge, and I can draw lines, electric field lines, right, for the charge. So I can draw it like this, 3 here, 4 here, 5, and 6, and 7, and 8. So I'm kind of drawing 8 lines there. Okay? So you have a charge, then field lines are coming out of this. Because it's a positive charge, the lines go from the charge to infinity. So field lines are going out of it. So what we say is that if you take this charge and then put that charge in a closed surface, the amount of lines, the amount of flux I should say, the amount of flux that is coming out of the charge would be equal to this charge Q, the flux that is coming out of it. Let's say this is phi, the electric flux which is coming out of the closed surface is equal to Q by epsilon naught. Okay? So this is what we say. We don't have this number 8 here, but in place of that number we have Q by epsilon naught. So that's the Gauss law, right? So now, but how do you calculate this phi, the amount of flux? Well, this is one way of doing it. Q by epsilon naught is the total amount of flux coming out of it. But then if you say, if I take this, for example, okay, if I take an imaginary sphere wherein I've kept that charge, then the flux through any small area on the sphere, on the surface area, any small area on the surface of the sphere can be given by delta phi E, the amount of lines which are coming out. Okay, it can be given, it's equal to E, the electric field strength on the surface multiplied by, or the dot product of that as these two x vectors. So this is going to be this vector dot product, and it's going to give you a scalar value is E, delta is cos theta, and that's the value you're going to get, and that value will be equal to the amount of lines, the amount of flux which is coming out of that small area. And if you do it for the entire area of this imaginary sphere, then I should be able to get this. So the entire area, we do it for that. So that is coming through this flux, the flux coming through this small area, another area, small area, another small area, another small area. If we add all the flux coming through all these different areas, then I'm going to get the total flux which is coming out of the sphere. Right? So that would be equal to integral E naught ds. Okay? So, or you can say the sum of small areas. Some of all these, some of the flux coming from all these small areas. So that's the meaning of that. Okay, or I can in discrete terms I can write this sigma E dot delta S. Okay, so this is what it is. So if you want to find flux through any small area, and this is what I do. I find E on that area, the electric field's intensity there, E dot delta S. That's the amount of flux coming through that area. If you add it all together, and this is what I get. So this is your vectorially, you're mathematically representing a very simple concept. Very simple. You take a charge, you keep it in a closed surface, then the amount of lines, the amount of flux which is coming out of the charge is not going to change. It's as simple as that, right? So whether you keep it in a sphere, whether you're keeping it in a box, whether you're keeping it in a cylinder, doesn't matter. Even if you use a cylinder here, for example, okay? Think about it. So the amount of lines, 1, 2, 3, 4, 5, 6, 7, 8, the amount of lines which is coming out of it, cylindrical shape is also 8. Because the number of lines which come out, it depends on the charge, but not on the shape of the closed surface you've taken. Okay? So that's the idea. But you can also imagine something else actually. I've kept the charge there. I kept the charge at the very center. So it's kind of like evenly distributed, right, along the surface. Like it's like this. If you take a charge and I keep it at the very center of a sphere, then the number of lines will be evenly distributed along the surface. Right? But suppose I take the charge and take it closer to one side. Okay? Like this. Suppose I'm going to draw a sphere like this. Maybe I'll use a different color. Okay, so now the center of the sphere is here. Okay, and the center of the sphere. Note that 1, 2, 3, 4, 5 lines come from this half and only 3 lines come from the other half. Previously, when it was centered like this, 4 lines come from one half, 4 lines are going through one half, and then 4 lines are coming to the other half. So then when I just move it here, 5 lines go through one half, and then only 3 lines go through the other half. But it doesn't matter. But the total number of lines would still be 8. So that's what we're trying to say. So that the total number is equal to Q by epsilon naught, and that's the flux, and that would not change. Whether you have a sphere and then you keep the charge in the very center, or you take the charge to one side of the sphere, doesn't matter. The only difference is that field strength will be greater here when it is closer, so that's why you get more lines there. Okay? And the field strength will be smaller here because this surface is a little farther from the charge, so you have less lines through that surface. But effectively, if you take the total amount of flux through the entire surface area, it will still be equal to Q by epsilon naught, irrespective of the shape or the position of the charge inside that enclosed surface. Okay, so that is the idea you need to understand. Okay, so it's simply the Gauss law can be written like this: the sum of E dot delta S is equal to Q by epsilon naught for the entire surface. So I is equal to 1 to it completely. Or I can say that closed surface integral of E dot ds is equal to Q by epsilon naught. I can write it either way. So why do you have this circle here? Because it's a closed surface integral. The closed surface integral, the surface integral then of E dot ds will give you Q by epsilon naught for the entire surface. The flux through the entire surface will be equal to Q by epsilon naught. So this is Gauss law. Okay, so understand that, and let's start doing a problem. Let's do an example problem that illustrates the idea of flux through a surface. The example is 1.11. Then let me read the problem for you. The electric field components in figure 1.27 are Ex is equal to alpha x to the power half, Ey is equal to Ez is equal to 0, in which alpha is equal to 800 Newton per Coulomb meter per half. then calculate the flux through the cube and the charge within the cube. Assume that A is equal to 0.1 meter. Okay. So it's like this. Let me try to explain the problem first and then we'll go on to do the problem. So this is example 1.11. First, they've given you a surface, a Gaussian surface. So these surfaces are called as Gaussian surfaces because they're closed surfaces, okay? Where you are going to apply the Gauss's law, right? Let's see. The Gaussian surface here is a cube. So I've got a cube here. And the size is this. This is A, and this is also A. And this must also be A. And it has 6 sides, and each side will have an area. And each side will have an area vector, right? Okay. Then what is the direction of the area? That depends on the outward normal. So that's the direction of each area. So if we take this area for example, the direction of the area is here, it's outward normal. So what's the area? A into A square in this direction. And what about this area vector? A into A square in this direction, right? And then what about this? Then A into A square in this direction. Okay. So these are the normals. Likewise, like if we take this side, then that will be in that direction. Right? We have a cube. If we take this side, the normal vector will be, the area vector will be in this direction because normal is in this direction. If we take the bottom side, then the area vector will be down because that's the outward normal. Right? And if you take the back side, then the normal will be in that direction. Okay. So that would be the direction of the area. So now I've found the area of this cube. Right? And what are they saying now? Well, this is fine, but then they also talk about the electric field in the space. Okay. Then how do they define the electric field? Well, there is the electric field E must have 3 components because we're talking about 3-dimensional space. So there must be an Ex and then Ey and then also Ez. Okay. So they say, okay, so it must be a vector sum of Ex plus Ey plus Ez. So what it means is that if the E is like this, then I should be able to resolve it along the X direction and then the Y direction and also along the Z direction. So that I should be able to do that. That's what it means. Okay. Suppose if this is the surface and if E is like this, then I should be able to resolve this along X, Y and Z direction. It only makes things easier for me. Anyway, so this is it. But they also say that this E, and they give you the value for all these components. Right? Okay. What is Ex? Ex vector is actually, there is a constant alpha into root x in the I direction. Okay. So that's the vector we talk about. Okay. And Ey vector is 0. So there is no y component for that vector, E vector. And then what about Ez? And there is no z component also for E. So E vector, the electric field vector has only one component, which is in the x direction. So the E vector is in the x direction only. It is not inclined either in the y direction or in the z direction. So its E vector is along the x direction. Okay. But then it also depends, the value of the E vector depends on the distance from a certain origin. Well, they say that this is the this is the origin, basically. Okay? This is x direction, and this is y, and then this is z. Okay? And this is the origin, and then the cube is at a distance of a from the origin. So if I take this point, then it must have one e value. And if we take this point, it will have a different e value, because you see from the origin the x value will be different. And inside also will be changing. The field value will be changing inside too. Okay? So that is what is given. E depends on x. E is not constant. If x is increasing, E will also be increasing. Ex will increase. If x is increasing, Ex will increase. Because Ex increases, E will also increase, because E is effectively Ex only. There is no y and z component. So that is the problem. So now you need to do the total flux coming out of this surface. Okay? Well, so how do you do it? Well, the total flux coming out of this surface, I call it as phi E, and that must be equal to, I'll call this as surface 1, and then this as 2, and then this as 3, and bottom as 4, and this side as 5, and that side as 6. So I need to calculate the amount of flux coming through this surface, and this surface, this surface, this surface, this surface, all the surfaces, and I should be adding them to get the total flux, right? So phi E is actually equal to flux through the first surface plus flux through the second surface and flux through the third surface and so on. Then I'll put it completely. Flux through the fourth surface, as flux through the fifth surface, and the flux through the sixth surface. It's a scalar quantity. I should be able to just sum it up. Okay? So this is what I'm going to do. Now, how do I find it? Well, first, flux through surface 1. Flux through surface 1, phi 1e is equal to E at that point, right? E at that point, E1 dot, then delta S1, this surface vector. We talked about it. So this surface will have a vector in this direction, right? In this direction, that's the direction of the vector. But I call it as delta S1, so I'll call this delta S1 vector. Okay. And then there would be an E vector here at this point, depending on this value. Then E dot delta S1 will give me the flux through that surface. Then what is the E1? Well, E1 vector is equal to Ex1 vector, right? Because there are no other components. So when I add E vector, Ex plus Ey and Ez, Ey and Ez are 0. So E is effectively equal to Ex only, right? So effectively I can say that E vector, the field, is simply Ex only. Then Ex at this point is what I need to find out. Ex1, then dot, then delta S1. Now what is Ex at that point? Well, for Ex, I have this expression. The magnitude is alpha into root x. Right? So it is actually alpha. And what is root x? From the origin, what is this distance? What is this distance? That is a plus a, 2a. So alpha into root of 2a. And which direction? E is in the I direction, right? Anyway, that's what we said, right? So E in the I direction. So I dot, then delta S1. What is delta S1? Delta S1 is simply a squared is the magnitude, and what's the direction? I only, because the outward normal is in the I direction only for this surface. So that is a squared to I. So this is a vector and this is a vector. The dot products I dot I is what I'll get. So AB cos theta, right? I'll get AB cos theta. Now this is my A vector magnitude, this is my B vector magnitude. AB cos theta is simply alpha into root 2A into A squared AB cos theta. Theta is 0 because I is in this direction and so the delta S is in this direction, E is also in the direction, so they are parallel to each other, so the angle between the two vectors is 0, so cos theta is 1, so that's what I get. So this is what I get now. So I can make this as this too. Alpha into root 2 into what is A squared into A power half, right? A power 2.5, or I can say A power 5 by 2. Okay, so that is a flux through the surface. I mean, I can put the numbers here, but I can put the numbers later. Okay, alpha root 2 A root 5 by 2. Okay, so that's what that is the expression I have here for the flux through the first surface. But let's take the second surface, phi 2e. Phi 2e. So that must be, I must have E2, the field value here, E2, the vector, E2 vector here, and E2 vector dot delta S2 vector. Okay. But so what happens there? What happens there is E2 vector is simply again Ex2 vector dot, so delta S2 is, delta S2 is what? Delta S2 is actually A square into this J vector. But E2 x vector is not as here, it's going to be in this direction. Sorry, the area vector is in this direction, the Ex2 vector is in this direction, because the field is always pointing in the x direction. So the angle between them, the area vector and also the E vector is 90 degrees, so this dot product will always be 0. So there is no flux through this surface. That is understandable because E is this way and your A is this way. There is no flux which is coming out of the surface. There is no part of flux which is coming out of it. It's only grazing through the surface. Nothing coming out of it. So it is 0. And mathematically you say that this vector is in this direction and this vector is in this direction. The angle between the two vectors is 90. So the dot product will always give you 0. So phi 2e is actually 0. There is no flux through this surface. So let's take phi 3e. What are you going to get now? Again, that is this surface, right? The front surface. Front surface. Again, E is in this direction and the normal is in this direction. Notice there 90 degrees to each other. So the flux through this surface is also 0 because there is no flux coming out of the surface, it's only grazing through the surface. Okay? So grazing over the surface, I should say. So phi 3e is also 0. There is no flux through the surface. And what about phi 4e? Well, phi 4 is border, right? So border is like this. Then the surface vector, the area vector is like this. But then E vector is only in this direction. So again 90 degrees. So the dot product will give you 0. So phi 4e is also 0. Okay. Which is to say that there is no flux through this. You can imagine this, like all the E's are like this. So there is nothing coming out of these surfaces. It's coming through this surface now. Okay. So phi for E is also 0. What about phi E? Phi E. This surface. Well, yeah, we take this surface. Well, E is in this direction, alright, wonderful. And this surface is in this direction. Okay, so now you have, it's not 90 degrees, it's 180 degrees now. E is in this direction, the flux is going into the surface. If you take the other surface, this side, the flux is coming out of the surface. But now the flux is going into the surface. Okay, so you get a negative number here, clearly. Okay, so phi E is actually same E phi vector dot delta S phi. Okay. And what is E phi vector? Well, E phi is in this direction, but then it is at this point. Well, that is going to be equal to E x at phi dot delta S phi, and that should be equal to what? That should be equal to vector Ex phi, that's alpha, and what is this distance from the origin? What's the x value? X value is A only, so that is the value of E at this position. So it's going to be root A, not root 2A. Root 2A, this was root, E was root 2A here. Here, I'm sorry, yeah, yes. Here, this surface, E had a root 2A component, but this surface, at this position, it will have only root A part to it. So, alpha, that is root A. And which direction? Well, it's in the I direction. And what about the surface now? Delta S phi. It's going to have A squared, that's the magnitude. And the normal is going to be in the opposite direction. So it's in the minus I direction, not in I direction. That's in the minus I direction for this surface. So I'm going to have minus I. Okay. So that will give me okay, you'll get minus I can take out, minus alpha root A, and then A square and I dot I, minus alpha root A square I dot I. I dot I is 1, as you've seen. So we go to minus value, negative value there. So I'm going to have this is equal to simply minus alpha, this is A squared, and then it is A power half, so A power 2.5, and is simply A power 5 by 2, okay, and into 1, so minus alpha by 2. So now this is the value here. Okay. What about phi 6? Phi 6E. What am I going to get now? Well, that's the other side, right? The other side of the cube. Well, E is still in this direction, and this vector is going to be this way, 90 degrees to E. So phi 6E will also be 0. So again, there is no flux coming out of the surface, but only grazes over that surface. 0. So I got phi 1E, phi 2E, phi 3E, phi 4E, phi 5E, phi 6E. Now, if I want to find the total flux through the surface, I must be adding all these things here. I should be doing this. So total phi E is equal to this. I get alpha root 2 A to the power 5 by 2, then phi 2 is 0, and then this phi 3 is 0, then phi 4 is 0, and phi 5 is again minus alpha a to the power 5 by 2, then phi 6 is also 0, so that gives you simply alpha root 2 a to the power 5 by 2, and minus alpha a to the power 5 by 2. Okay, so this is what you get. Now you come here, take the common things out, and you get alpha to a to the power 5 by 2, take it out, and I get root 2 minus 1. So this is a flux. This is a net flux through this surface. Okay. Now, in the problem, they've said that alpha is 800. Value of alpha is 800, and then the value of A is 0.1. So you put it out, and then you're going to get, the actual value. So alpha is 800 into A is 0.1 to the power 5 by 2. Okay, and then root 2 minus 1. Root 2 is 1.414 minus 1. 0.414. So multiply this, we are going to get the total flux through this. Okay, now this is nothing but Newton meter squared per coulomb. So that's the flux you're going to get through the entire surface. So you calculate the flux through each surface area. Now you put it all together, so now it's got a closed surface. So flux through this side, this side, this side, this side. You're adding all the fluxes together to get the total flux coming out of this surface. So the total flux is found to be this one. I'll get this value. So that's the part A of the problem. And then part B of the problem is, what is the charge inside them? What is the charge inside the closed surface? Okay, now you know this. What is the charge inside the closed surface? That's easy. It's very easy, because you see, what does Gauss law say? So the B part of the problem. What does Gauss law say? The total flux coming out is actually equal to Q enclosed by epsilon naught. The enclosed charge in the surface, the closed surface, divided by epsilon naught. So Q enclosed is equal to epsilon naught into phi e. We got phi e here, then you know the value of epsilon naught, then multiply those two, then you will get the charge now contained in the cube. Okay. So that's very easy for you to do. So I'll take that. Epsilon naught is 8.854 into 10 to the power minus 12, and phi e is again 800 into 0.1 to the power 5 by 2, and then into 0.414. So you multiply this all, then I'm going to get a certain amount of coulomb there. So this is how you do this problem. Okay? So I want you to understand this again. So what we have done here, we have taken a surface, we have assigned directions to the different areas of the surfaces, okay, of this closed surface. Now we found the E value on each surface, then found the flux through the surface by taking the E value and doing a dot product of that vector with the area vector. So it will give you the flux through that area alone, that surface area alone. So we found flux through different surfaces, added them up to find the flux through the entire closed surface, and we know that that must be equal to Q by epsilon naught, and from that we can find the charge enclosed in that surface. Okay? So this is how you do this problem. Hope this is clear to you. Okay, let's do one more problem. Example 1.12. An electric field is uniform and in the positive x direction for positive x, and uniform with the same magnitude but in the negative x direction for negative x. It's given that E is 200 I Newton per Coulomb for x greater than 0 and E is minus 200 I Newton per Coulomb for x less than 0. A right circular cylinder of length 20 centimeter and radius 5 centimeter has its center at the origin and its axis along the x-axis so that one face is at x is equal to plus 10 centimeter and the other is at x is equal to minus 10 centimeter. Then what's the net outward flux through each flat face? Then B, what is the flux through the side of the cylinder? Then C, then what's the net outward flux through the cylinder? And D, what's the net charge inside the cylinder? Okay, so that's the problem. So it's like this. It's example 1.12. So an electric field is uniform and in the positive x direction for positive x. So I'll use a different color. It looks like let's say, let me take okay. So this is the coordinate axis. Now it's like this. The electric field is along the positive x direction. It's constant. It's constant. This is the origin. On this side, you have E is equal to 200 in the I direction. So it is always in this direction on this side. That's E. And it has a constant value. On this side, same, but then it has the same magnitude, but it is in the opposite direction on this side, the negative x direction. But again, it's constant. So minus 200 I. So if this is the origin, the field is 200 units in this direction. And again, the same 200 units in this direction, constant. Now, what's the question? The question is, a right circular cylinder of length 20 centimeters and radius 5 centimeter has its center at the origin. Okay, now I am going to have a right circular cylinder whose center is at the origin. But you see, the radius is 5. The radius of the cylinder will be 5 centimeters. But then on this side, I am going to have 10. I am going to have 10. And then on this side, I am going to have 10. So it's like this. Okay? The cylinder, something like this. The center of the cylinder is the origin, and the cylinder has a radius of 5 centimeters, and the total length of the cylinder is 20 centimeters. But since it is centered at the origin, this side is going to be 10, and this side is going to be 10 centimeters in length. It's kept like that. Yeah. Now the question is, what is the net outward flux through each flat face? Okay. Now if you take that cylinder, if you take this as a cylinder, this is the flat face, and this is the flat face. So you need to find the flux through this flat face and this flat face. That's the first point. But then you see, you also have this surface, the cylindrical surface. Okay? You can think about it straight away, first of all. Okay? First of all, what is the flux through the cylindrical surface? see, E is in this direction only. So, is there any flux coming out of cylindrical surface? No, it cannot. Right? No flux can come out of the cylindrical surface because E is only in this direction and this direction. So, E is in this direction, but if we take this surface, normal is like this. So, normal at every point on the surface is going to be 90 degrees to E. So, the flux through the surface, through the cylindrical surface, this curved surface of the cylinder will be 0. But there can be flux through the flat surfaces here. So, that's something that you can see because E is flowing in this direction, it's also in this direction. It's like a pipe, like you have at the center, water is coming out and then it is flowing through this side and this side. So, water is not coming through the other side. I mean, the curved surface, it is not coming through that because it's going in this direction and this direction. It's like that. Yeah. So, coming to that, I can say, I need to find the flat surface. What do I need to do? E is in this direction now, and then E is in this direction now. Now, how do I find the flux now? So, this is, I call this as surface 1, this is 1, and this is 2, and the flat, the curved surface is 3. Okay, let's see. What is my phi 1? Phi E1 flux through this must be equal to E1 flux in this direction dot delta S1. Right? Okay. Now, what is delta S1? So, delta S1 is actually this area, the flat area. So, that will give me pi r squared, right? So, pi r squared will be this area. And this side, this is outward normal. So, the outward normal will be in the x direction. So, if you want to find delta S1 vector, it's going to be pi r squared in the I direction. Right? The positive x direction, because that's where the outward normal is. So, what is 3.14 into r is actually 5 centimeters, what is it, right? So, 5 by 100 square in the I direction. Okay? So, that's my delta S1. But what about delta S2? So, delta S2 is actually the same, but on this side, right? On this side, the same pi r squared, but the outward normal is now in this direction. So, it's in the minus I direction, in the negative x direction. So, delta S is the same pi r squared. This delta S2 is the same, it has the same magnitude pi r squared, and then it's going to be in the minus I direction. So, the delta S squared vector is actually minus 3.14 into 5 by 100 square I vector, okay, the negative direction. So, you got delta S1 and then delta S2. Okay. Now, let's see what is E1. E1 is simply 200 I in this direction only. Right? So, we got 200 I dot this one 3.14 into 25 by 10 power minus 4 I. Okay, so this is going to be about so I got 2 I dot I. I can take I dot I. I dot I will be 1. Right? I dot I is 1, or I can say A, B, cos theta. So, this is A, this is B, cos theta, theta is 0 because delta S is in this direction and E is also in this direction. So, theta is 0, cos theta will be 1. So, I can do it that way also. If you do that, anyway, this I got 200, 10 power minus 4, I get 10 power minus 2 there, and then 2 into 20 is 50, 50 into 3 150, 150 into 14, 0.14 into 50. So 7, right? So it's I'm going to get 157 kind. 200, but I take 2 into 3.14 into 25 into 10 power minus 2 to 1. I dot I is 1. Okay, 200, 10 power minus 4, 10 power minus, that's what I will get, right? Now it's 50 into 3.14. So it's going to be 3.14 into 5, right? Do this way. 0, 157. Okay, so 15.7, right? So 15.7 10 power minus 2 or 1.57 into 10 power minus 1. No. 50, right? Okay, so 157, it's going to be 1.57. Right? So Newton meter squared per coulomb. So that's the unit, that's the phi E1. And then what about phi E2? So phi E2 also equal to E2 dot delta S2. So E2 is 200 in the negative I direction, so minus 200 into I dot delta S2 is going to be minus same 3.14 into 5 squared by 5 by 100 squared I direction. So minus will become plus, then I'm going to, and I dot I will become 1, so I'll have the same number 1.57 Newton meter squared per coulomb. See, doesn't matter. What are you trying to figure out now? How much flux is coming out now? If the flux is coming out, then it's a positive number. So on this surface or through this surface, flux was coming out, so you get a positive number. And through this surface, flux was coming out, so you also get a positive number here. So even though this is in the negative direction, area is in the negative direction, E is also in the negative direction, you are going to have flux coming out, so it becomes positive. Negative and negative will become positive. Okay, so if flux comes out of a surface, then you get a positive number. If flux goes through a surface into the surface, and you get a negative number. Okay, so that's the thing. So you got both of them. And what about phi E3? So phi E3, so that is this surface, and if I take the E is in this direction, but then you see if you take every point, it's going to be 90 degrees to E. So no flux is coming through this curved surface at all. So flux through this curved surface is actually 0. So the total flux phi E is equal to phi E1 plus phi E2 plus phi E3, and that gives you 1.57 plus 0 plus 1.57, so that gives you 3.14. Okay. So 3.14 Newton meter squared per coulomb. So that's the total flux coming out of it. So if you know the total flux coming out of it, can you calculate the charge contained in this, enclosed in the surface? Easy, right? So you know phi E is equal to Q enclosed by epsilon naught, and therefore that gives you Q enclosed is equal to epsilon naught to phi E. So that is going to be 8.854 into 10 power minus 12 into 3.14 Newton. Okay, if you do that, it's going to be Coulomb, right? Ultimately. So this is 9, this is 9, and then it's like roughly 3, about 27. Okay? So I'm going to get about 27 into 10 power minus 12 Coulomb, or I can say the 2.7 approximately equal to 2.7 into 10 power minus 11 Coulomb. So that's a charge Q enclosed. Amount of charge enclosed on this. So this is how you calculate this. Okay, so what have we done here? We have found the flux through this surface, and we have found flux through this surface, and then we have also found flux through the curved surface of the cylinder, and we added it all together to get the total flux coming out of the cylinder or going into the cylinder. In this case, flux is coming out. So you get, because you get a positive number here. So you found the flux, the total flux coming out of this closed surface of the cylinder, and you also found, using Gauss law, the charge enclosed in the surface. So that's what I've done here. Hope this is clear to you.